We'll continue looking at some of the problems here. So we looked at some of these. When we have gases, like all these are gases here, we could either express it in terms of Kc or Kp, the equilibrium constant. And we can quickly see if Kc and Kp are numerically going to be equal. And so here, would Kc and Kp be equal? You can tell by delta N of the gas. Is delta N of the gas, was there any change? No, so they're equal. And look at this. This is the reverse of the formation reaction that we were looking at, double the formation reaction. So NO is quite unstable. You can see that NO rapidly decomposes into N2 and O2 here. Or I shouldn't say rapidly because it depends. Speed of reaction is related to kinetics, and driving force is related to thermodynamics. So even though we might have a driving force, we really can't say much about the kinetics. However, when there's a huge driving force, it usually happens pretty quickly. This would have a huge driving force. Kc 2.1 times 10 to the 30th would bring this close to like minus 200 in terms of kilojoules per mole on the delta G. Looking at this next reaction here, we could use Kc or Kp. However, Kc and Kp are not going to be equal because over on the left we have 1.5, over on the right we have 1. The calculation between Kc and Kp is fairly straightforward. So sometimes it's more convenient to use molar concentration. Sometimes it's more convenient to use partial pressures in the bar. And so that'll dictate it. Now, when we calculate K using thermodynamics here, we call it KEQ, that is the equilibrium constant. And so KEQ, or K, is not equal to Kc here. And so if I wanted to get Kc, I usually have to do an additional calculation. So in this particular equation here, from delta G, I could calculate Kp. From Kp, I can calculate Kc. And so there's some steps involved. These all have a temperature, and so there's going to be a temperature at which those are valid. And so let's take a look at K and temperature here. That was in chapter 13, so we go back to chapter 13 for. So we know that delta G varies with temperature. So one way we can figure out what the K or how K varies is to calculate delta G at a different temperature and then use that delta G to calculate K. So in other words here, we know that delta G varies with temperature. And so we can calculate delta G at different temperatures, understand the conditions, and use that to solve for K. Okay, that's if we know the temperature. If we're trying to solve for the temperature, it makes the equation a little bit more complicated because we can't solve for delta G if we don't know what the temperature is. So this is the delta H, delta S equation, this one here, and we're trying to solve for temperature. And so rather than solve for delta G, we have to use the delta H minus T delta S. You can see these terms here equate to. Right? And then we have this equation here. There are different ways we can see. So we can't solve for delta G directly because we don't know the temperature necessarily. And so that's why we got that equation here. But we could also use this equation to relate that K varies with temperature. And we have this equation, delta G naught is equal to minus RT ln K. But if we want a K at a different temperature, we can't use this. So we have to use this. Using this, then we solve for ln of k. So just divide by minus RT, both sides. So delta H divided by minus RT gives us minus delta H over RT. And then T delta S, a negative, divided by minus RT gives us a plus delta S over R. The T's cancel here. So it's just simple algebraic rearrangement. And then we have this equation here. This equation looks kind of similar to what we saw for the Clausius-Clapeyron equation, where we can calculate the partial pressures at different temperatures. Well, we can do the exact same thing for this. The exact same thing is we can get this into Clausius-Clapeyron form. And how did we get the other one? The Clausius-Clapeyron form is we don't do the curve, we don't do the line, with the logarithmic plot. What we're going to do is we're just going to calculate one value at temperature T1 from another value, temperature T2 or vice versa. And so what we did was we used that little trick with the logs. Do you remember what we did for the Clausius-Clapeyron? Yeah, right, the subtraction. That's what I'm talking about. And so I'm kind of curious about delta K and temperature. And then this is going to be from chapter 13, in case we need to calculate different K values at different temperatures. It varies with temperature. And we know that delta G naught is equal to minus RT ln of K. And therefore, if we want to solve for K, we could get this in typical form. K is equal to e to the minus delta G naught over RT. Do it in that form. Or we could just leave it in natural log form, similar to Clausius-Clapeyron equation. So if we do that, we go ln of K is equal to delta G naught divided by RT. And this whole thing is going to be negative. Is that correct? But we're going to be restricted because delta G naught is a function of temperature, and K is a function of temperature. So it depends. We can calculate the delta G naught at different temperatures. And so one way of figuring out K at a different temperature is just plug in here. I think I wrote this equation up earlier. But there's an alternative thing that we can do as well. And the alternative thing is, okay, this is going to equal delta H naught minus T delta S naught divided by RT. And so this is going to simplify into what we saw earlier, that is minus delta H naught over RT plus delta S naught over R. We're going to get here. Then we can do this thing. We can do the ln K at T2 minus the ln of K at T1. Okay, so this is going to equal minus delta H naught over RT2 plus delta S naught over R. Okay, minus delta H naught over RT1 plus delta S naught over R. All right, so what we're going to do is we're just going to simplify this here. So this is going to come out to minus delta H naught over R over here. Do you see the delta S naught term is going to cancel? And we're going to get 1 over T2 minus 1 over T1. Does that look familiar? Well, that looks familiar because that's a Clausius-Clapeyron equation. And in the Clausius-Clapeyron equation, what is K equal to? In the Clausius-Clapeyron equation, we're taking A liquid goes to A gas. And if we look at K for this, K is going to be the activity of a liquid, or a gas, plus first, where the activity of a liquid first is K2 over K1. And so what is the activity of a gas approximately equal to? The activity of gases is equal to the partial pressure of the gas in the bar. What is the activity of pure liquid? 1. So K is just the pressure. So an example of using this equation is more applicable. But if we just look at only vapor pressure, then this equation, we derive this equation from that. And that is Ln of P2 over P1 is equal to minus delta H of vaporization over R 1 over T2 minus 1 over T1. And so one of the applications of this equation is to derive the Clausius-Clapeyron equation. So we just derive the Clausius-Clapeyron equation here. But we could use this for other. This is just a specific application, but we can use this for other calcs. So we don't have to use this for vapor pressure. We can use this for whatever we're interested in. And so K is going to be a function of temperature. And so when I look at the homework here, that's missing. And let's see, did they give it to us here? I don't know if they derived it. So do you see ln of K? Do you remember seeing ln of P? Can you make that connection? We got that plot. And then do you see this? This is the exact same thing as chapter 12. Exact same thing. And so here we go. Keep in mind that the Clausius-Clapeyron is just a special case of equation 1325. Okay, let me open another window here. So we need to know the temperature, because K varies with temperature. And so normally we specify the temperature for the K's as well. But the K value there, is that a KP or KC from that equation, or from chapter 13? Or KEQ? It's a KEQ. If you have all gases, it's a case P. If you have all solutions, it's a case C. But what if you have mixed? So let's talk about mixed. If it's a solid plus all solutions, then it's a case C. If it's solid and all gases, it's a KP. But if you have a solid plus solution plus gases, then it's neither. KEQ. It'd be KEQ, right? And so we'll take a look at that. Let's see some KEQs here. So an example of that, would be this one here. Well, no, this one is solid, solid, gas, gas. So KP is fine for this. That would be KEQ. We could also do this in KC. And so we could do this as KP or KC. Let me give you an example of one that is going to be mixed. So if we look at calcium carbonate, which is solid, plus 2 HCl for aqueous, this is going to go to calcium chloride, which is aqueous, plus CO2 gas, plus H2O liquid. So if we try to do this as a KP, the only gas we have is this. So KP is not going to work. If we try to do it as a KC, then what do we do about the gas? You know, the gas is in different volume, although the gas does have pressure. I mean, and also a concentration is possible for the gas. And so the best is for a KEQ. KEQ is going to be the activity of the products. So the activity of the solution is going to just be its molar concentration. The activity of CO2 is just going to be the pressure of the CO2. Activity of water is just 1. Divided by the activity of calcium carbonate, which is 1. The activity of the solution is HCl. That's going to be squared. And that's it. So this is going to be a mixed. We're going to have concentration and pressure.
I say you have like a liquid like ethanol. What would the activity be?
1. If it's pure.
Pure liquids are ethanol.
Yes. If it's 95% ethanol, then you have to calculate the molarity.
Okay. And then that would be concentration.
Right. All right. We can experimentally determine the equilibrium constants. So I gave you some. And we don't have to measure all the equilibrium concentrations. We can just measure some of them and then figure out the others. And so let's see which one I was looking at. Okay. So some of these we use a little bit of stoichiometry to determine the, like say for example this number 18, 1 gram of H2, 1.06 grams of H2S. So we can calculate how many moles of H2, how many moles of H2S. And then they tell us the equilibrium amount of S2. There was no S2 initial, and so we have to use a little bit of stoichiometry to figure out how to generate that amount of S2. So some of the H2S must be decomposed. And so once we do that, in other words, ice tables missing items. So typically it's happening. You can figure out what the missing items are because they give you enough information to figure out the change. And so sometimes some items are missing. So if we have this, A plus B goes to C, and they give us A, and they give us B 0, and they give us C initial, and then they tell us B final. Then we can figure out everything here because it depends on the stoichiometry here. You know? And so in this particular case, we have the balanced chemical equation, which is 2 and 1 and 2. So this is 2, 1, and 2. And so this has got to be plus 2x because we'll go to the 0, the side with the 0, plus x minus 2x. And so 0 plus x is this. And therefore we can figure out what x is. From x we can get these. And so we just fill in the rest of the table. That's pretty much all of these problems. You know, you're given part of the ice table, you fill in the rest of the ice table. Pretty much. Sometimes it gets confusing because if you look at number 21 here, you know, write the equilibrium constant expression for the following reaction and compute the equilibrium concentration of iron 3+ at pH 7. So we can do this one. I don't know if this is number 21 in the 11th. I think this is number 21 in the 11th edition. We get that again. So this is just filling in the ice table. Write the equilibrium constant expression for the following reaction. So this is going to be mixed. You know. Obviously, this is solid because it's hydroxides are all insoluble. So they expect you to figure that out on your own. I don't know why they didn't show it. They should have shown it. This is balanced. And so the equilibrium constant expression is just the activity of the product of the iron 3. To the first. And then we have H2O liquid, so that's 1 cubed, so this is 1. And then we have solid, that's 1. And then we have H plus, which is going to be cubed. And compute the equilibrium concentration for Fe3 plus, pH 7. So at pH 7, so we have to figure out what the H plus is. The H plus, they say, is 1.0 times 10 minus 7 molar. And so if we were to do the table, let me just do the table here. What do we do about a solid? Solids and liquids appear in the ice table. And the answer is no, because the concentration, that is the activity, does not change. And so what we do when we have a pure solid like this is you just draw a line through each entry for that. Maybe I'll just write it down here. We'll just rewrite this. We have our iron 3 hydroxide solid plus 3H plus. This is a metathesis reaction. Essentially, the net ionic equation for metathesis. Here, and so initial, pure solid, no. Pure liquid, no. So the only thing we're interested in is H plus and Fe3 plus. The change, there's going to be no change in the concentration. We're going to lose some or gain some, but in terms of the activity, there's no change. You know, as long as we have some there, there's going to be no change in the activity. And so we just need to fill in the rest of the table here. Now, the rest of the table here is, and compute the equilibrium concentration for iron 3 plus at pH 7. So this pH 7, the H plus, is that initial or is that equilibrium? And so this is the question we have to answer here. I or E? Um, okay, they say at pH 7. So if we started at pH 7 and it's initial, then the pH is going to change because H plus concentration will change through the course of the reaction. And so by the time we get to equilibrium, then that means the pH had changed. And so we want it at pH 7. So if it's at pH 7, that must mean it's at equilibrium. So we know that this is going to be 1.0 times 10 to the minus 7. And therefore, what we need is we need the iron 3 plus concentration. Well, we don't need the rest of the ice table for this. Because if we know that this is equilibrium here, then that's fine. We're going to get K is equal to the iron 3 plus concentration at equilibrium divided by the equilibrium H plus concentration cubed. So this is 1.0 times 10 to the minus 7. So this pH 7 is neutral, and this is going to be cubed. And so we know what K is. K is this. This favors the right side, and we just solve for this. So, Then we have equilibrium relationships. Relationships I talked about the first day. You know, if I reverse the equation, K is inverted. If I add equations, we multiply the K. Then we convert. So for example, we might want to convert Kp and Kc, so we just use the equations for that. And so these are like Hess's law style, but they're different because the rules are different. And so Kc, Kp conversions, and then adding equations, and that kind of stuff. All right, then the next section deals with direction and extent of chemical change. Direction of the change is given by Q. You know, is Q equal to K? Is Q less than K? Is Q greater than K? We can get the direction. The extent of chemical change is like the percent. You know, how much did it react? So we can get the direction. So, for example, here, 31, they give us this reaction here, and they tell us the moles, and they tell us the volume, so we can calculate molarity. They tell us Kc, and so we just calculate Q and compare it to K. If Q and K are equal, then the mixture is at equilibrium. If not, then if it's bigger, it's going to go backwards. If it's smaller, it's going to go forward for the Q. So those are QK problems, not. Just do a few of those, and you'll be fine. And what we're going to do is we're going to do something a little bit more complicated here. We're going to look at number 40. And, number 40 is like a Le Chatelier's problem, but in Le Chatelier's, we typically do those qualitative, you know, what direction is it going to shift? This is a quantitative Le Chatelier's problem. We're going to shift it. We're going to perturb the equilibrium and then determine what happens and what the final state is going to be. So, I mean, this involves the N2O4 NO2 equilibrium. If you look at the K, which is more favored at 25 degrees C? NO2 or N2O4? The K is small. So N2O4 is more favored at 25 degrees C. What would happen if I increase the temperature? What do you think is going to happen? Increase the temperature at constant pressure. Yeah, NO2 will become more favored. One, you were breaking bonds. You know, it's endothermic in the fourth. I mean, we could recalculate the K, you know, if I wanted to recalculate at 50 degrees C, I could recalculate it using that equation and just plug in chug that equation. But we're going to keep the temperature at 25 degrees C. How we're going to perturb this is we're going to change the volume. Which side favors larger volume? Which side favors smaller volume? Yeah, right side favors larger volume. We have 2 moles of gas. So what we're going to do is we're going to take this. This is going to be at equilibrium, and we're going to increase the volume. If we increase the volume, there's going to be a shift to the right. There are different ways. That's Le Chatelier's. Le Chatelier's favors side with bigger volume, with the side with more moles of gas. The other way we can look at it is based on Q. What happens to Q? You know, what happens to concentrations? Now, what if both sides have the same? Well, if both sides have the same, then it makes no difference. The ratio of concentrations remain the same. It's not going to upset Q. But if both sides aren't the same, then if I change the volume, it impacts one side more than the other in terms of concentration. So we'll just take a look and see what happens here. So we're going to take N2O4 and go to 2NO2. NO2s. Now, we have the initial. Sometimes we could use initial amounts, that is moles. So if we had equal 2 and 2, then it doesn't matter. I could use mole or molarity. But if they're different, then I can only use molarity. I can't use moles because the volume doesn't quite cancel out. And so they give us moles here, but I have to calculate the molarity. So for N2O4, I'm going to have 0.971 mole per 0.750 liters. And then I need to calculate the molarity of that. 0.971 divided by 0.75. 1.29. I'm allowed 3 sig figs. I'm going to carry one extra. So this is going to come out to 1.294. Maybe I'll carry 2 extra. The reason I'm going to carry 2 extra is because I want to calculate my Q, and I want to calculate more precisely so that I can see it's indeed at equilibrium. I don't want too much round off error, in other words. And so the molarity of the NO2 is going to be 0.0580 over 0.750 liters, and this is going to give me molarity. So 0.058 divided by 0.75. 0.0773. You know, a lot of calculators are doing these fractions. Fractions are used to prevent rounding error. So maybe, depends on yours. Let's discontinue on. So let's calculate Q. This is my initial conditions. So Q, which is the initial, is just going to equal NO2. This is QC, by the way. This should be a QP, but I got a KC here, so I'm just going to go with QC. I could calculate the pressures of the gas too, just using the ideal gas law, but I'm not. If I was given KP, then I would have went straight to pressure here. But since I'm given KC, I'll just go straight to molarity. So I'm then just going to take it. It's going to be the concentration of NO2 squared divided by the concentration of N2O4. These are the given, and so let's go ahead and calculate it. I'm going to just take the last calculation, square that, divided by 1.2946. And I get this. I get 4.619 times 10 to the minus 3. In other words, I got 4.62 times 10 to the minus 3. Am I at equilibrium? Well, to be at equilibrium, I need 4.61. So I'm a little bit too big, which means it's going to shift to the left, right? But this was supposed to be at equilibrium. So we're going to pretend that this was at equilibrium. And this is just due to rounding. Let's say that. So I have a system at equilibrium, but what I'm going to do is I'm going to perturb that. And so this is Le Chatelier's principle. I'm going to perturb it by increasing the volume. And increasing the volume is going to screw up things because the volume is going to impact this more than that. And so I'm going to add another 2.25 liters to my 0.75 liters. And so the total volume is going to be 3 liters. And so the way that this impacts it is I'm going to perturb it. So I'm going to set a new initial condition. And the new initial condition is going to be 0.971 moles over 3 liters. So 3.00 liters. And so my new molarity here is going to be 0.971 divided by 3, 0.3236 molar. And then this volume is going to get perturbed too, and so I'm going to have 0.0580 moles over 0.750 liters.
3 liters.
Yeah, right, 3 liters. Which gives us a molarity of what? .01933. So this is the original, which I'll call 1. This is going to be initial conditions 2 after perturbing this. And so let's go ahead and calculate Q once again. So this is going to be 0.0193 squared divided by 0.3236. 1.15 times 10 to the minus 3. So Q is going to be less than K. If Q is less than K, what's going to happen? There's going to be a change, and it's going to shift which way?
Right.
Shifts right. Well, that's what we predicted based on our qualitative analysis of this. Increasing volume favors this side with more moles of gas. But what we're going to do now is we're going to do this quantitatively. And so what we're going to do is we're going to have our initial 2, then we're going to have a change. It's going to shift right. So this is going to be minus x molar. This is going to be plus 2x molar. And so therefore at equilibrium, I'm going to have 0.3236 minus x. And this is going to be 0.01933 plus 2x. And then what I'm going to do is I'm going to just go ahead and plug that into my K equation. K is equal to 4.61 times 10 minus 3, which is going to equal 0.01933 plus 2x quantity squared divided by 0.3236 minus x. Do you know what order this is going to turn out to be? Second order. So second order is a quadratic. So we can go ahead and do the quadratic. But I want to use a trick. I want to use a trick to simplify the math. So would the simplifying assumption work very effectively here? I don't think so. This math is a bit too much, because I could do something to further simplify it. What can I do to further simplify it? Well, I could do the simplifying assumption, but the x will drop out of both. You know, you could maybe do the simplifying assumption on 1, the denominator. You wouldn't want to do it in the denominator in this case, because the initial, take a look at the initial in the numerator, it's much smaller than the initial in the denominator, even though the change is 2x versus the change of x up here. So you might try it in the numerator. But there's another trick that you can use. What is the other trick that you can use? Reset. And so this one is favored reactant or favored product?
Favored product? Oh, no, it's reactant.
Reactant? Yeah, K is small, so product is favored. So what I'm going to do is, it's a bit too much. What I'm going to try to do is reset the initial. So I'm going to go to initial 3. And what I'm going to do is I'm going to get rid of all this. And so here, initial 3 means I'm going to skip this here. And I'm going to go minus 2y. Minus 2y is minus 0.01933. And then over here, I'm going to go plus y. And so that's going to be, y is going to be half of this. So what is half what we got? And so let's do plus 0.01933 over 2. And so my new initial condition will be this. I'm going to take, that's the ratio. It's a 1 to 2 ratio. So I'll go 0.3236 plus 0.01933 divided by 2. So my new initial here will be 0.3332 molar, and my new initial here will be 0 molar. The more zeros I have, the less algebra I have to do. And so that's another reason I like to reset. And so I'm not doing as much algebra. Now the change is going to be in the direction of the 0. So this is going to be minus x molar. This is going to be plus 2x molar. And so at equilibrium, I'm going to have 0.3332 minus x molar. And over here, I'm going to have 2x molar. So now let's look at K again and compare here. K is going to equal 2x squared, quantity squared, divided by 0.3332 minus x. Which one of these two would you rather solve for the quadratic? If you need to get this into quadratic form, which of these two would you rather solve to get into quadratic? Obviously, the second one, right? It's going to be a lot easier. So we can set that equal to 4.61 times 10 minus 3, and then we can get this into quadratic form. And then we can use our calculator to do it. And so to get this into quadratic form, I'm going to go ahead and do that here. This is going to equal 4 squared. Okay, then I'm going to multiply this by both sides here. So I'll take my 0.3332 times 4.61 times 10 minus 3. And so that's going to give me, this is going to be times that. So, and then I'm going to subtract it. So it's going to give me a minus 1.536 times 10 to the minus 3 over here. And this is going to be plus 4.61 times 10 to the minus 3 x is equal to 0. And then I'm going to use the quadratic solver on my calculator. And so the quadratic solver it's going to ask you for A, or if you're at home and doing homework, you could just bring it up online. There are a bunch of quadratic solvers online. So A was 4, B is 4.61 times 10 to the negative 3, and C was, I forgot what C was. Let's take a look at C. Negative 1.536 times 10 to the minus 3. Negative 1.536 times 10 to the minus 3. All right, now I have the two roots. You know, if I got the direction of the change wrong, the negative root would actually be correct. Now, let's say I said, oh, it went the reverse direction, and I picked the wrong direction, then the negative root gives me positive. But in general, it's if you pick the direction correctly, it's always going to be the positive root. And so again, x is equal to 0.019028. All right, then let's plug it back in here and then see what the concentrations come out to. So I'm going to have 0.332, 0.3332 minus 0.019028. I carry extra digits here because when I do the double check, I don't want round off error to throw me off. And rounding error can throw you off. It might be just because you're off just because of rounding, or it might be you're off because of calculation. So I want to try to eliminate the rounding option and just have an error due to calculation. And then double this, which will be 2 times 0.019028, 0.038056 molar. Now I have way too many digits, but the reason I have way too many digits again is to minimize rounding error when I double check my K. So I'm going to square this number I just calculated divided by 0.3141. And I get a K of 4.6108 times 10 to the minus 3. So that's good. That checks out. And so here's where we did it shifts it to the right, but here's where we did a quantitative calculation of Le Chatelier's versus a qualitative. And we used one trick. The one trick was just to decrease the number of binomials to make the algebra easier. Now we have KPs. The KP calculations are exactly the same as the KC calculations. The one difference is sometimes they're going to ask you for the total pressure. What is the total pressure? The total pressure, remember Dalton's law? Total pressure is the sum of the partial pressures. And that adds one more equation, to all the equations that we have. And so sometimes we have a system of equations where we have to use the total pressure in order to figure out some of the partial pressure. And so if we look at this one, we have 747.6 millimeters of mercury pressure, and 1.85 grams of iodine are introduced in the flask. What will the total pressure in the flask be? So we calculate equilibrium pressures and then stat amount. So this one's not too bad. There are other problems where they give us the total pressure and ask us to solve for some other stuff. But that's not too bad because we just use Dalton's law in conjunction with our ice table to figure things out. So you can take a look at these problems here. Then we have Le Chatelier's. These are qualitative Le Chatelier's. Now, if we change the volume, does that change K? Like in the last problem, we changed volume. Did it change K or did it stay at 4.61 times 10 minus 3? It stayed the same, actually. If we change the concentration, does that change K? It changed Q. Q changed, but K did not change. If we change temperature, does that change K? Yes, that changes K, but it's in the predictable fashion. And the predictable fashion is this. Higher temperatures favor endothermic. Lower temperatures favor exothermic direction. And so that's how we can tell how K changes. So let's look at number 64 here. For which of the following reactions would you expect the extent of forward reaction to increase with increasing temperature? So if we look at this, if we increase the temperature, which directions favored? The endothermic direction. So can you tell me which direction's endothermic in reaction A? To the left. So increasing temperature will favor the left. What about increasing volume for reaction A? Increasing volume favors, they're equal, so there's no change. Increasing total pressure. Increasing total pressure is going to impact them equally because I have 1 mole of gas on the left, 1 mole of gas on the right. So increasing total pressure is like the volume. There's going to be no change. Increasing the partial pressure of NO. That should change it. Which way? I'm going to have too much NO. If I have too much NO, I screwed up the ratio. Now I have too much NO. Which way is it going to shift? To the right. Increasing partial pressure of O2, only O2. Which way would it shift?
Would it stay the same?
No. Even though the N2 didn't increase, having more O2 means it's going to attack some of the remaining N2. And so it's going to shift to the left. And so I don't have to increase both of these. I can just increase one. And as long as there's some N2 left, then more of it will shift to the left. And that's pressure and concentration. Concentration is the same thing. If I increase the concentration, O2, it shifts left. You know, it screws up the ratio.
How does increasing the partial pressure like add the rubber? Isn't it just
It changes the activity of it. And so it's like, yeah, same. If you only do one of them, you know, if you increase the partial pressure of all of them, then it's not going to do anything. It's going to be the same. But you're going to make one side more active. And now, how do you increase the pressure? So if you increase the pressure at a fixed volume, then you're increasing the concentration of that, and it's one way of thinking about it. But basically, it's the activity, you know, and so that's going to drive the reaction more, one way or the other. Yeah. All right, those are Le Chatelier's. Let's look at number 65. The following represents the binding of oxygen by the protein hemoglobin. Hemoglobin has an iron 2 stuck in the center. So it forms, this is the coordinate covalent bond here that they're trying to show. It's binding to hemoglobin here. Explain how each of the following affects the amount of this complex. This is what we call an adduct. Does anybody remember that word, adduct?
I remember you talking about it.
Yeah. Sometimes you'll hear that. So this is a Lewis base adduct. Lewis base adducts are common. Or you don't have to call it that necessarily. Increasing the temperature. If we increase the temperature, does it favor more binding or less binding? Less binding. Yeah. Versus endothermic. Breaking the bond here. This is a coordinate covalent bond we're going to break. It's pretty weak. This coordinate. Oxygen is not a great ligand, not a great Lewis base, so it forms a pretty weak bond. And that weak bond is critical because you have to break it off. Otherwise, you're not going to be able to use any of the oxygen that the hemoglobin transported. B, decreasing the concentration of O2. So we decrease the concentration of O2, which lowers its activity, which is going to shift it to the left. You know, it screws up the ratio. C, increasing the amount of hemoglobin. So hemoglobin is not pure, it's aqueous, so we're increasing the concentration of hemoglobin. If we increase the concentration of hemoglobin, it will shift it to the right. Yeah. This one's a bit tricky because, you know, it could be the same concentration. So you have 1 liter of 1 molar versus 2 liters of 1 molar. You know, they're both going to have the same activity. In the human body, the enzyme carbonic anhydrase catalyzes the interconversion of CO2 to bicarbonate by either adding or removing the hydroxide anion. So anyway, we'd have to draw this out, and then we can see. This is an acid or base, and so if we have hydroxide, we'll neutralize this second H from carbonic acid, or this H and then convert it to CO2. And so this is very similar, just Le Chatelier's problems. We have a bunch of those.
And this is all 15, so we're not going to be testing
I'm not going to have two tests on the same, but we're going to have the test on 15 pretty soon, probably the following week. So when we have very small and very large K values, you always need to reset. Otherwise, your calculator could fail. And so just remember, if it's very small, reset it to the left. If it's very large, reset it to the right. Yeah. Do you recognize this NH2 minus? What's that? Amide, right? And amide, what do you know about one of the chemical properties of amide? What chemical property stands out?
very strong.
It's a very strong base, and strong bases hydrolyze water completely. So we say that this reaction happens 100%, but does it really happen 100%? Well, when we look at the K value, the K is 10 to the 20th. So that tells us it doesn't happen 100%. In order to happen 100%, the K would have to equal infinity, right? And so what we can do is we can do a calculation. We're going to calculate how much amide remains in solution, at 25 degrees C. And when we calculate how much amide remains, we'll get a concentration there. And then they ask, is the result physically meaningful? So let's say the concentration that remains is like 10 to the minus 16 molar. In order to get one amide ion, how many liters of solution do you have to have if it's 10 to the minus 16, And so that's what they're asking. They're asking this. Is it feasible if you had 1 liter of this solution, would you expect to find any amides in there? And then there's some integrative advanced, I think I assigned 76 here. Radioactive tracing is very common. Carbon-14, they can make this with a specific isotope and trace it because they can see where it ends up using like a Geiger count or some other radiation detector, and then see how the carbon-14 distributes. Does it distribute evenly, or is it biased towards one side or the other? Sometimes these isotopes are biased because of their weight, and that's called fractionation. It's a big topic in geology. And there's some more problems. We did one of these. Sometimes we make these are called like engineering equations. Engineers love this. I was taking an engineering class. They like to break it down into a simple equation like this and use plug and chug. It is much faster that way. But, how do you derive this equation? And so we can come up with equations like this that show, how much, or this type of stuff, or that type of stuff. So like this, for example, this would be like an example of engineering equations. So we take, all the equations that we have, and then we try to combine them into a new equation, and we get something like this. And then we use that equation. So for example, here in 88, it asks you to use the equation from exercise 87. And so that's common, but sometimes when you have engineering equations like this, you got to keep track of the units and that kind of stuff. And so there have been some big mistakes made, and so there's more equations like this. I didn't really talk about these. I mean, if you do a lot of these calculations, you want a simple equation like this. But if you don't, then you're just going to derive the numbers as we did. This is talking about the activity. Is the activity of pure solid or pure liquid really 1? We're assuming it's 1. And so in 97, the activity of pure solid or liquid is approximately A. This is the equation for activity. So if you want to calculate activity, you can plug in chug here. Where V bar is a molar volume. For pure solid or liquid under typical conditions, the quantity V bar, etc., is quite small, primarily because V bar is small. And so the activity is approximately equal to 1. Use the following data for liquid water at 300 Kelvin to verify the activity is approximately equal to 1 over a wide range of pressures. The data are from the CRC Handbook of Chemistry, Physics, 83rd edition. And so what we can do is we can calculate the activities for each of these and then just show it's about 1 all the way across. But you see it's not perfectly 1, you know. So we make these approximations here to make our calculations life a little bit easier. Here they're just showing this. You know, we got 5 nines, 99.999% if K's 10 to the positive 10. So in case 10 to the positive 10, that's a lot of product. So it's 99.999% reaction. If K is 10 to the minus 10, that's very little product. 0.001% reaction. So we want to know like percent reaction. So this is another reason to reset. So that's how in chapter 15. We'll take a look at those problems there. And we're going to move on to chapter 16 today. Chapter 16 is more basic equilibrium calculations, except for weak acids and weak bases. For strong acids and strong bases, we just say it goes 100% pretty much. Unless it's like amide. I mean, we could calculate it, you know, but is it really necessary to calculate it? Well, in Chem 1B, we're going to calculate it. And so that last problem, you know, with the amide, we're going to calculate it. But anyway, let's take a look. And so the first thing is when we do acids and bases, we got to look at pH. So you might have covered pH in Chem 4. We covered it briefly in Chem 4. But acetic acid, if you look at this equation, acetic acid and weak acid, it partially. Well, that's qualitative. That's like the Chatelier's principle. What we want is quantitative. How much does it ionize? Well, we need a Kc value for this. You know, what's the Kc or the K value for this? K and Kc are the same. Well, it's really easy. You know how we do it? We use a pH meter. You know what a pH meter measures?
The amount of H+.
Yeah, the amount of H+, and that's at equilibrium. So if we stick a pH meter in there, we have the equilibrium concentration of H+, and then we can fill out the rest of the ice table. It's pretty easy. So if we start off with 1 molar acetic acid, that's what we had, and that's what we mixed. We can figure out how much H+ formed by using a pH meter, and then we can fill in the entire ice table based on that. Once we get that, then we can solve for Kc. Once we get the Kc, then we can compile that into a table. And the table is going to be what we call a table of acid ionization constants. So let's take a look at the table here. For acetic acid is so common, I haven't memorized. It's 1.8 times 10 to the minus 5. But they're compiled over there. If you take a look at the acid chart there, I'll look for acetic acid on the right side, second from the top. It's 1.76 times 10 to the minus 5. So most people round that to 2 sig figs, called 1.8 times 10 to the minus 5. That is because water has a difficult time plucking this off. It's not polar. It has a harder grip on that hydrogen. So it can't pluck it. So it comes out to like 99.99% unreacted, 0.01% reacted, something like that. We're going to calculate percent. But the weird thing is it changes. So at 1%, we have, at 1 molar, we have a certain percent ionization. At 0.1 molar, that percent ionization actually goes up. And so the percent ionization of the acid, that's weird. Here's another one. Here's the base ammonia attacking water. This is called Kb. The previous one is called Ka. A stands for acid hydrolysis, B stands for base hydrolysis. And so when we do acid and base calculations in water, we're doing Ka and Kb. Here's a hydrated hydronium ion. And so the hydrated hydronium ion makes an H11O5 plus species. And so this thing behaves as one unit. This is because this hydrogen bonding interaction is strong. It kind of forms this cluster. And so we get a cluster. This isn't completely covalently bonded to one another, just this big cluster, and this cluster is going to have this composition. And so some people say, well, H3O plus isn't entirely accurate because we get different clusters forming, but it's okay. We're going to go with H3O plus. That's for acid hydrolysis. H plus alone is not stable. And so here, this is acid hydrolysis. And so we'll take a look at these now. What's the name of that acid? Yeah, the top one. Yep, good. Chlorous acid. This is acid hydrolysis. Hydrolysis means splitting up or breaking up of water. So this is acid hydrolysis. What's the acid? Chlorous acid. What's the base? Water. Water's amphoteric. It goes either way. And so we call this a Ka. So the Ka is going to equal the hydronium concentration equilibrium times the, what's the name of this anion? Chlorite. Chlorites make chlorous acid. Divided by the chlorous acid concentration. Divided by the water. Now, does the water concentration change significantly? Water concentration is actually pure water. In pure water, the concentration is 55.5 molar. You know how I calculated that? Pure water, 55.5 molar, because there are 55.5 moles of water in a liter. A mole of water, a liter of water weighs 1,000 grams. And a mole of water is 18 grams. So 1,000 grams divided by 18 grams gives us 55.5 moles. Now, if I dissolve a little bit of chlorous acid in there, is it going to change the concentration much? It does change the concentration, but does it change it by much? No, I mean, even if I put 1 mole in there, it doesn't change that much. And so it stays relatively constant. We can include that here at 55.5 molar, but essentially the activity is 1, so we exclude it. And so this is what it looks like. And so this is called acid hydrolysis. Let me write that down again. And so if we take an acid, this is a generic acid, HA, A is the anion, and react it with H2O liquid, we're going to end up with hydronium and A minus. And in case of A standing for acid ionization or acid hydrolysis, is going to equal H3O plus times A minus concentration divided by the HA concentration. This is standard. Likewise, if we have a base, we're going to have base hydrolysis, like amide did earlier. And the base is going to either be B or B minus. Or actually, I should do A minus. Sorry. Let's do A minus. It doesn't have to have a charge. You know, it could be neutral like ammonia, but it could be charged like A minus. And so base hydrolysis is going to look like this. It's going to form HA plus hydroxide. And so acid hydrolysis produces hydronium, base hydrolysis produces hydroxide. When we have base hydrolysis, we form Kb. Kb is going to equal HA times hydroxide divided by A minus. Water is pure liquid. We have something like this. Now, these are conjugates. Do you see the conjugate pairs? The conjugate relationship. So HA and A minus are conjugates. And water and hydronium are conjugates as well. And A minus and HA, these are conjugates. And water and hydroxide are conjugates as well. This is water acting as a base. So if water acts as a base, what is its conjugate acid? It's hydronium. And this is water acting as an acid. If water acts as an acid, what's its conjugate? Hydroxide. And so this is the acid here, this is the base here. This is the base here, this is the acid here. And so we have to get familiar with the conjugate relationships because there's something interesting that happens with Ka and Kb. Check this out here. When we have Ka times Kb and their conjugates, these have to be conjugates. So for example, A would be the HA and B would be the A minus. Then this is equal to this. So just multiply it out. And so we get the hydronium here times the A minus divided by the HA. Okay, times the HA here times the hydroxide divided by the A minus. Here. And we look at what cancels out. The HA cancels, the A minus cancels. And what does that leave us with? That leaves us with this. It's equal to the hydronium concentration times the hydroxide concentration. Well, this thing is called Kw. Because water can go either way. And so let's talk about Kw now. If water acts as the base and another water acts as the acid, then what are we going to form? Well, let's say this one acts as the base, we're going to form hydronium, and this one acts as the acid, we're going to form hydroxide. We're going to form hydronium and hydroxide. And so K for this is equal to the hydronium ion concentration times the hydroxide ion concentration divided by 1, right? Because 1 times 1, the activity is pure water. So, this is a weird equation. You know what this is equal to? This is equal to Ka for water, which is equal to Kb for water. So water can go either way. This is the Ka for water, the acid hydrolysis, but this is also the Kb for water, the base hydrolysis, because the acid and the base are the same thing. And so that's what we call Kw. And so this is called water hydrolysis, or we just call it water autoionization. We can measure the pH of pure water. At 25 degrees C. Do you know what the pH of water at 25 degrees C is?
7.
Yeah. pH is equal to 7.00. And then we can do the ice table for this. So we're going to do the ice table. So we're going to have water liquid plus water liquid. This is going to go to hydronium plus hydroxide. And what we're going to do is we're going to do the ice table here. What do we put for liquid water? Nothing. And then what we're going to do is we're going to reset this mentally. So here, this is a mental reset here. We're going to assume that none of the waters have collided yet. No H2O molecules have collided yet. And then what we're going to do is we're mentally going to turn on the temperature or the collisions, the kinetic energy, and allow these to collide. So this is going to be plus X molar, plus X molar. And so then at equilibrium, we're going to get X molar and X molar. But we know the pH, and this is the pH. This is going to be the H plus concentration, which is equal to the H3O plus concentration, since H plus and H3O plus are the same thing, essentially, which is going to equal. Now, when we do this, we take the inverse log, and what this is going to come out to is it's going to come out to 1.0 times 10 to the minus 7 molar. Here. And so what we see here is this is what we call 2 sig figs, and this is the power here. And so we end up with 2 sig figs here. And so that's why I put 1.0 in the front here. And so this comes out to 1.0 times 10 to the minus 7 molar. And that means hydroxide has to be the same, stoichiometrically. 1.0 times 10 to the minus 7 molar, which means that Kw must equal the hydronium times the hydroxide, which is 1.0 times 10 to the minus 14. There's no units here for Kw. Now, power functions, we'll talk about next. Okay. Oh, yeah. All right, thanks. Okay. So I'm going to stop here. You don't have to prepare for Monday's lab. We're just going to do Monday's lab deals with acids and base hydrolysis. And so we'll just go through it together. No, just leave some blank pages. The test will be on Tuesday. Yeah. Boy, I don't bunch up the tests too much. Oh yeah, turn in the lab from last week. Forgot to collect that yesterday.